Okay, so I'm sorry I can't be there. My wife is having surgery today, so I'm going to miss F and G blocks today. So you have a reading assignment. It's section 8.2, questions 1 through 6 on page 262. So you should know where to find the PDF. The PDF is in unit resources for unit 3. Now we're going to talk about notes today on acids and bases, okay? And this is a little bit of a mistake in the objective. This is not the last reaction type, but we will do that in the next set of notes, but this is going to still give us 3 more reaction types today. Now, how do we classify this reaction? Take a look at it. It might look kind of familiar, okay? It kind of looks like we've got something with 2 parts and something with 2 parts, making something new with 2 parts and something new with 2 parts. It looks like a double displacement reaction. It actually is, and it's also, of all things, an acid base. And we're going to have to talk about what an acid and a base is. Anything that begins with a hydrogen ion, we already know is an acid. We know how to name it from the nomenclature unit. Anything with an OH, as you'll see, is a base, and we'll go in through and define that a little bit better. But the key thing here is that this is an acid base and a double displacement reaction. Now, these reactions are a little bit hard to detect with the eye, okay? You can't really see very easily water being made, and it's kind of tricky also to tell the temperature change because it's fairly subtle. So what I've done is I put together a video. It's demo number 1. It's in the notes, all right, under notes and handouts, that shows how you can tell, and I did this video for the other classes, how you can tell whether there's a reaction by measuring the volume very carefully and measuring the temperature very carefully. So if you want to see that, go through and look at the video. Okay, so that should help you realize that yes, we can see that water is made, and yes, we can tell that there's a temperature change. Now, what is the driving force for this reaction? It's formation of water. Okay, you don't need a solubility table to predict this type of double displacement reaction. As long as you have an acid and a base, it will always make water and a salt. And in chemistry, all a salt means is an ionic compound. Now, what are acids and bases? Okay, the easiest definition is by this Dutchman named Arrhenius. It's very simple. An acid is a substance that forms hydrogen ions in water. Here is hydrochloric acid. If you put it in water, it breaks apart into hydrogen ions and chloride ions. A base is a substance that forms hydroxide ions in water. So typically the way we think of a base is it's got to have an OH in the formula. If you put it in water and it breaks apart, it's a base. So you make hydroxide ions. Now, this definition is the simplest one. It doesn't really work real well if you don't have any water around, but most of us have water around, so it works fairly well in a classroom setting. So we can tell whether we have acid or base. Now, there's 2 kinds of acids and bases, okay? They're either strong or weak. So you are going to have to memorize the strong acids and the strong bases. The reason why we're memorizing the strong is because there's only 6 strong acids and there's only 8 strong bases. There are literally hundreds, if not thousands, of weak acids and weak bases. So let's memorize the easy one and then realize everything else that isn't strong is weak. Okay? There's a little bit of help. Chlorine, iodine, and bromine are all halogens, so they're all in the same group. Sulfuric acid we've used quite a bit in reactions when we're writing them out, so you might be familiar with that. The 2 that are harder to remember are perchloric acid and nitric acid, okay? Every other acid is weak. The classic example here is acetic acid. Acetic acid is found in vinegar. Vinegar is about 5% by mass to volume acetic acid. Now, we can actually, eat salad dressing that's got vinegar in it. You can't eat salad dressing if it had hydrochloric acid substituted for acetic acid. It would actually basically cause a chemical burn to your mouth and your esophagus. So weak acids are much less reactive, as you'll see, than strong. Now, let me also give you the list of the strong bases. Now, these are actually not that bad. Remember, everybody has an OH group to be a base. Lithium, sodium, potassium, rubidium, and cesium are all the alkali metals with a hydroxide attached to them. Remember, they're all 1 plus, OH is 1 minus. And then the other three are barium, strontium, and calcium. Go over to the alkaline earth metals. The top two are not strong, but all the rest are. Now, I did leave off francium hydroxide, and I left off radium hydroxide. Okay, we're never going to deal with those compounds. Now, all other bases are weak. If you want an example, magnesium hydroxide is a weak base. We used that before when we had that white solution in the centrifuge, and we were spinning down to show that you could separate the magnesium hydroxide from the water. It was a suspension. So magnesium hydroxide is found in Maalox, which is that antacid that's also a laxative. Anyway, it is a weak base. You can actually put that in your body and it won't hurt you, where all the strong bases would hurt you. So we don't eat those. Now, what is the difference between strong and weak? Strong acids completely dissolve into water, into hydrogen ions and an anion when dissolved in water. So here's an example. There's your strong acid, hydrochloric acid, completely breaks apart into hydrogen ions and chloride ions. Weak acids don't do that. They mostly stay together when we put them in water. Okay? So here, take a look. On the left, this is a strong acid. So if the gray ball or sphere is H plus, and the green sphere is the negative part, like say chloride, you can see they're all broken apart in water. On the right is what it would look like if you had a weak acid. Do you notice that the negative part and the hydrogen stay stuck? So for instance, if it was acetic acid, the H stays stuck to the acetate ion. But every now and then, one breaks apart. So if you had to sketch it, strong, everybody's broken apart. Weak, maybe one breaks apart. Now, if you look at strong bases and weak bases, the drawing is going to look really similar to this. The labels are just going to be different. So take a look. Do you notice I actually use the same beakers? I just now say that the gray is hydroxide, and you'll see it's the cation. So here, sodium hydroxide is a strong base. There's your hydroxide, and the green ball or green sphere would be sodium ions. On this side, if it was a weak base, for instance, the purple ball could be like magnesium, and the gray balls would be the hydroxide stuck to it, and you'd only see like one broke apart. Okay. Now, detecting acids and bases. One easy way to tell them apart is to use litmus paper. Acids turn litmus paper red. Okay. Bases turn litmus paper blue. And so litmus paper is an indicator that changes colors in acid or base solutions. In water, okay, litmus paper isn't going to change. So it comes in two flavors, red or blue. I put together a very short video of something we did in class where we tested 3 solutions and tried to figure out which one was water, which one was an acid, and which one was a base based on the color of litmus paper. So yes, this is something you need to know, and you should watch the video. That one's really short. Okay, that's demo number 2. Again, it's found in notes and handouts. It's right after the notes for the number 5 notes. Predicting products of acid reactions. So this is pretty much where we're heading. This is the last little bit. Now, acid plus base, the demo that I did at the beginning that you can look at the video of, you saw that water was made so the volume increased and some heat was given off. That's true of every acid-base reaction. An acid plus a base will always make some sort of a salt and water and give off heat, okay? So the temperature will go up a little bit. It only went up about 3 or 4 degrees Celsius, but the temperature will go up. It is a double displacement reaction. It's a subtype of double displacement called acid-base. Sometimes we call it a neutralization reaction. We can actually put that in. Okay, we can also put that in, that's fine. Okay? Now, the complete ionic equation is written here for this reaction. Do you notice that everything still just breaks apart into ions? We have to put in the state symbols, we have to put in the charges, but what doesn't break apart is the covalent compound water. It doesn't break apart in ions. It's sort of like the insoluble solid of the double displacement reactions that are precipitation reactions. And if we look at the net ionic equation, take a look. For every one water formed, we need one hydroxide and one hydrogen ion. Now, this is a very simple reaction. Sometimes you might have two hydroxides reacting with two hydrogens, and guess what that makes? Two water. If we had six hydroxides reacting with six hydrogens, that would make six water. You'll notice that the coefficients always have to be the same. You always need equal numbers of hydrogen ions and hydroxide ions, and they'll make an equal number of liquid water molecules. Here's another reaction you need to know, acid plus metal. Here's hydrochloric acid with magnesium, making magnesium chloride and hydrogen gas. You can see acid plus metal makes a salt and hydrogen gas. This has got three different reaction types. I like ones with three. Hint, this is clearly a single displacement reaction. Acid plus metal, that's an acid, that's a metal, and it's also redox, so oxidation reduction. Look, here magnesium has an oxidation number of 0. Here magnesium ion has an oxidation number of +2. Here the hydrogen ion has an oxidation number of +1, but here it's elemental hydrogen, it's got an oxidation number of 0. So magnesium has lost electrons, so it's oxidized, and hydrogen has gained electrons, so it's reduced. Now, last reaction, acid plus carbonate. A carbonate, by definition, is anything with a CO3 group. Baking soda is sodium hydrogen carbonate, anything with a carbonate. If you react it with an acid, you're always going to make water, carbon dioxide, and some sort of a salt. Here, since I picked hydrochloric acid and sodium carbonate, we're making table salt. All right? So acid plus a carbonate makes water, carbon dioxide, and a salt. Okay? Acid plus carbonate. So a carbonate is an ionic compound containing a CO3 2- group. Remember, that's a polyatomic ion. So if you see that with an acid, all right, it's going to react. Take a look. You've got two driving forces. You've got formation of liquid water, and you've got formation of a gas. You've got two different things that are driving this reaction forward. So it's definitely going to occur. You don't need any special table or anything. Acid plus carbonate reactions always occur. If we were to try to predict this one, sulfuric acid with calcium carbonate, we could figure out it's got to make water. And what else has it got to make? It's got to make CO2 and a new salt. So if this is calcium, it's going to make calcium sulfate. Oh, look, calcium sulfate, water, and CO2. Okay? Now, that's it for the notes. There was a worksheet that you're going to need to fill out. Ms. Azaris Davis was going to hand it out during, at the beginning of class. It's basically sketching, going back, let's see, sketching a strong and weak acid and base, and it's going to be very, very similar to these sketches, right? There's a strong acid, there's a weak acid, right? There's a strong base example, there's a weak base example. So you're supposed to sketch that inside the boxes on the worksheet.